so you asked about the final exam. I'll send an email about it, but it will, according to my email records, it's on May 17th. So that's in finals week, I think. Yeah. 9 a.m. And the room, it says, is room 528. So it's, what room is this? It's 528. Okay. It's probably.
This is 508.
Yeah, I think it's 528. Okay. Okay. So. Yeah. So then let's get started with the lecture. So we basically kind of completed most of really the kind of stuff that I wanted to kind of teach you, I guess, most of it, which was, you know, to get up to quantum algorithms. So we covered several types of quantum algorithms, and so I think, you know, that's enough knowledge for you to actually, you know, go and investigate further quantum algorithms if you like. Of course, you know, some of them are much more complicated, like we never did Shor's algorithm. That's one of the famous quantum algorithms, one of the most powerful, the one that can factor numbers and, you know, possibly break cryptographic protocols, things like that. But yeah, so I think we're not going to really do that because it's kind of more of the same thing. You know, we could go through different quantum circuits, but so I think for the remaining part of the course, what we'll do is just to go over a few of the sort of, you know, other central aspects of quantum information and maybe quantum mechanics in general. And so what we could talk about, or what I think is one of the more important topics to talk about, is how to introduce kind of noise into the system. So that's why I've drawn this little devil guy here. So the density matrix is a way of handling noise, and this is actually very important for quantum systems. Like if you want to build a quantum computer, then you really have to think about this because it's really quite hard to make a quantum computer. Basically, the main reason is actually this, that quantum states are really fragile, and you know, you might intend to do a particular type of quantum operation, but you might, you know, end up with something totally different. So making this hardware is hard for this reasons of basically noise. So this is the mathematical kind of framework of how to handle quantum systems with noise. So that's basically what this slide set is about, and then there's another slide set which we'll go through after this, which will be kind of how to use that. Okay, so that's basically what this is about. Okay, so I've already kind of introduced several of the ideas here, but just to repeat. So, you know, suppose we have this quantum computer. This is our sort of qubits inside a quantum computer, and just to give a specific example of what I mean by this, by noise. Suppose, you know, I have one qubit here, and that's prepared in this state. So we're trying to do some quantum algorithm, and then, you know, we create that state there. And suppose there's a duplicate version of that state over here too. You know, these are supposed to be the same, but due to various reasons, this state is actually not the same as this one, even though they're supposed to be. That was your intention. And this could be either because there are it's like noise in the system, and the noise kind of affects this one, say, and changes it from what it was originally, this one, turns it into something else. So it could be that, or it could be that what you did is in the gates that you use to prepare your system is actually not perfect. So you maybe every time you do your gate, it's only correct to within say 1% or something, right? So the second time you do it is exactly the same as the first time. So each time you do it, it's a little bit different, and basically your gates are your source of errors. So so basically, as I was saying, we need to be able to kind of handle this kind of situation. And yeah, and so there's this often word that gets thrown around, decoherence. So this is basically the same thing, but just to understand what this word means, because if you're ever talking about quantum computers and saying, and you're asking, so you've made a quantum computer, and if you want to sound intelligent or something, then you can say, what is the decoherence in the system? It's a kind of a phrase or word that a lot of people just throw around, and you hear it all the time when you're talking about quantum computers. So just to understand what this word means, so firstly, this word decoherence obviously comes from coherence, right? So we better understand what coherence means. So coherence is the effect of having basically some superposition of this state. So originally, coherence is used in the sense of essentially your waves. If you have any kind of wave property, essentially your wave nature is very well kind of intact. So a laser, for example, is a very coherent kind of light, because the light is the waves of the light are all in sync. This is what happens in a laser. So basically, it's synonymous with having a kind of a very pure type of wave, and because quantum mechanics, the main element is to sort of to have this superposition. So it doesn't really look like a wave anymore, but because one of the essential properties of waves is this superposition. So if you've got two waves, and you make a double wave, you have a wave and an anti-wave, and they cancel out. So this coherence, which is this superposition, is kind of the main sort of important concept in quantum mechanics or any kind of wave behavior. So any sort of alpha or beta would, so long that this alpha or beta is, they're not like 1, 0 or 0, 1. Any other state you would say that has some kind of coherence. So actually the only state that you would say does not have coherence are the states 0 and 1. And because these are the classical states, these are just your regular logical bits, for example. So you would say that these do not really have coherence because there's no superposition or anything. But anything else other than that would have coherence, right? Because it involves superposition. And okay, so that's what coherence means basically. It's it has some superposition. Right? So then, what is decoherence? Decoherence basically means that even though you tried to make this state with some coherence, something happened, some uncontrolled event happened with the environment, or maybe your gates weren't good enough, like I was saying, and randomly kind of changes to one of these states. So you lose that coherence, so hence decoherence. Your coherence is lost. So picture it something like this. There's some noise happening on the system and removes that coherence. Or put another way, this state sort of randomly becomes one state or zero state. And if you notice, this is actually a lot like measurement, right? So this is exactly what happens in a measurement. Actually, in the modern kind of way of thinking about it, decoherence is actually just basically the same thing as a measurement, in fact. And you just think of a measurement as something that you did, and you think of decoherence as something that you didn't want to happen but happened anyway. So it's just a difference between whether you did it or somebody else, well, not somebody else, but nature or just uncontrolled things happened to it. So yeah, so it's an interesting kind of way of thinking about it, but we'll see later that actually they are kind of mathematically equivalent, and you can write decoherence in a very similar way that you write measurements. We did measurement operators, and so it'll look very similar to that. But that's, this is a kind of an invention or way of thinking that this field of quantum information kind of really brought into popularity. So, yeah. Okay, so, all right, so let's start classically of thinking how do you mathematically describe noise. So if you think of a classical bit, and so in ancient times there used to be these things, hard drives, which we don't have anymore, but they worked by having small bits of basically this is a magnetic material, and this head here, what it does is to change little parts of this disk here and change the magnetization of that disk. And magnets are really good for storing information because magnets sort of always want to point all in the one direction. So if you think of these things as little magnets, then basically within that sort of little, looks like a little piece of corn. For one piece of corn, all the atoms want to sort of point in the same direction, and it's relatively resilient against losing that information. So, but it's not perfect, right? So, if you heat this thing up, then gradually this will kind of lose the magnetization, for example. So how do we kind of capture this piece of this kind of noise? So you can see it's not perfectly uniform, right? It's not totally black or totally white. So the way that we can think of it is just sort of with probability. So we could say that ideally, say a state is supposed to all be in zero. It's supposed to be zero state, but due to some noise, it will kind of, some of the time, it will flip to the one state, right? And so long that your noise is not so big, it's still going to be mostly in this zero. So maybe the way that you can think of this is like, so in your hard disk, say we're looking at like one of these, one of these says black means all the atoms. That's one bit of the data, right? And then so basically what's actually happening in there is that you have all these atoms, and the round things, the atoms, and this is the magnetization. So, so occasionally you're going to get one which is pointing kind of the wrong way. Maybe here is another one. So what this probability would describe is, and this would be, say, one bit of this hard disk. And what we're saying with the probability is that most of these guys are pointing up, but then there's going to be a couple which are pointing the wrong way. And it's kind of random which ones they are. Okay, so that's, you know, relatively okay theory to handle noise. And so how do we do this kind of thing quantum mechanically? And the problem here is that we know that, you know, if you have some wave function, then, like for a qubit, so of course, if you just look at that, then it's, like, you know, it's fine. But you know that these coefficients also involve some notion of probability, right? Because say you do a measurement, and with probability alpha squared and beta squared, it turns into these states, right? So there's the quantum mechanical probability, and what we're now trying to do is a different thing, which is to take into account of some kind of noise. And actually, they're two different things, right? So, so how do we take this into account? So, okay, so you know, this is the problem, and so that's what we're going to talk about. So how do we sort of think about this? So actually, we think about this in a very similar way to what I just drew on the board here. So suppose we have a bunch of qubits. So these are all individual qubits. And suppose we have some situation where, like, most of these ones are supposed to be in the same state. So that's why I've written psi, 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 psi. But then again, like in this case, there's like one which is kind of the wrong state because some noise acted on it. Yeah. So, so firstly, let's introduce some terminology. So if we have like quantum states without noise, so say this guy wasn't there, then, you know, and then we looked at just all the clean qubits without the noise. We basically would say that this is in a pure state because there's no noise, it's pure. Okay? Now, if there's some kind of noise here, and we have to sort of include this guy with the noise, then we call this one a mixed state. Okay, and so so let's try thinking about like how to take into account of this noise. Let's just have a try of doing it like this. So suppose, you know, there's like how many atoms here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. So there's 12 atoms here in total, and 1 out of 12 is, well, there's noise on it, right? So maybe what we could try is to say, okay, well, why don't we kind of try and define an average wave function of all these guys, and you know, as the probabilities, these are probabilities. So we can take like this one to be 1 over 12, and this one would be like 11 over 12. Okay.
Professor, I have a question. Because I think this should be p squared should be equal to the probability, right?
Yeah. Yes. So you're probably already realizing that this is not going to work. Okay. So let me just keep going because yeah. So this is just a kind of a straw man for saying that this is not the right way to do it. Okay. And you can see that this is not going to work because, well, okay, so I didn't do 1 over 12, I said half. But, you know, we run into some kind of conceptual problems if we do anything like this. Because, for example, if half of them were up and then half of them down, according to that, we're going to get like half of 1, 1. And then, okay, so firstly it's not normalized. I think maybe this is what you were just about to say. But also, it's a bit strange because it's like, okay, we have like half of these guys up, half of these guys down, and then half up, half down makes a plus state, but this doesn't seem right in the context of what we've learnt, because this plus state is some state which is supposed to be like a superposition of 0 and 1, right? And just having like half of these up and half of these down would, it just doesn't seem to make sense. So basically this doesn't really work. So this is an incorrect method. So, but doing things, I mean, when you do research, actually, this is the process that you take actually to work out the right answer. You first try it, just the first thing that comes to your mind. You look at it and you go, well, that looks completely wrong, and then you go, okay, but why is it wrong? So it's wrong because well, basically what we've now got is, what we're now trying to do is that we've got like the wave function, but we've also got probabilities, and those probabilities are more or less independent of the wave function. Right? So like these probabilities could have been anything actually, right? So I could have chosen 1 over 12 or half or anything. And this wave function is also anything, right? So they're actually kind of completely unrelated, independent things that you need to take into account. And if you write a state as this vector, we're basically already using all the degrees of freedom of this vector already, right? So if we've got n, dimension n, then these are complex numbers, okay? So there's 2n degrees of freedom. Okay, we need to have it normalized. So there's 2n minus 1 free variables. That's just to encode the wave function, right? And then if you want to add information about probabilities and noise, there's basically not enough variables to stick all that information in here. So we kind of need something with more variables in order to even describe the state. Right? So how many more variables do we need? Well, basically we need also n degrees more degrees of freedom, because just to encode probabilities. And because these probabilities, each of them have sort of n entries, roughly there should be sort of n squared degrees of freedom. Okay. Anyway, you need more degrees of freedom. That's sort of the point. So this is what you do. So this is the way that people have come up with to handle this situation. So we've been saying this whole time that states are vectors, right? States are vectors. And, if you want to do operations on the states, then those are matrices. Okay? And now we're going to throw that out the window, and we're going to say that no, states can also be matrices. Okay? So we've changed sort of something that we've been saying before, but okay, we need to do this to include this noise aspect. So, so this is what we do. So for a pure state, that's a state without noise, we're going to define now the state as this particular matrix. Okay? It's a matrix because it's, ket bra. Right? So it's the other way would be just a number. Okay, so let's get used to this idea. So for example, for a qubit, let's say that the pure state that we have is this one. Then, well, we can write this thing, and so this thing is now, we're going to call it the density matrix. Why is it called the density matrix? I don't know. Historical reasons. I can't really. I realize that I think I don't know why it's called the density matrix.
Because it's a very interesting name.
Okay, you think?
Yeah.
Okay, yeah. Let me think later if I can come up with a good reason why it's called the density matrix. Yeah, it might be something to do with probability densities or something like that. But yeah, I think at this point I'm not really sure why it's called that. But we're going to define it like this. And okay, so let's just write down what it is for this state. Fine. So we have that state. That's the kit for the state. This is the bra of the state. Don't forget the complex conjugate. Expand it out. Okay, so it's this thing. Or if you like, matrix notation. So if we keep the ordering of these things correct, this is a vector, this is a conjugate vector, and it's that. Okay, so these are clearly a matrix, and just keep in mind that so these density matrices now they represent still the state of the system. So even though we're writing it as some matrices, it's still a state. Okay, so there's a couple of things you can sort of already notice with this simple example. So first thing that we notice is that if we look at the diagonal elements of this, then as we know from the normalization of this state, this thing is going to add to 1. So it turns out that this is always true, even for the more complicated examples that we're going to do later. The diagonal elements of the density matrix always add to 1. And this is somehow analogous to the normalization of the wave function. So it comes from the same place. So the more general statement is that the trace, sum of the diagonal elements, is always equal to 1. Another observation is that the density matrix is Hermitian. That means that complex conjugate transpose is the same matrix. Diagonal elements, obviously, because they're diagonals and they're real. Off diagonal, you interchange these and you just have a difference in the complex conjugate. So these guys are always just different by complex conjugate. So it's Hermitian, but actually, even more generally, I'm not really going to state any proofs or anything, but this is actually a positive operator, which basically means that all the eigenvalues are bigger than 1. Sorry, bigger than 0. Yeah. And also the eigenvalues also sum to 1 too, which is actually the same thing. And finally, if we look at the off-diagonal elements, I talked about coherence before, right? And for the case of, say, the state 0, so if psi is 0, then this corresponds to a density matrix of 1, 0, 0, 0. Or if psi is 1, then the density matrix is 0, 0, 0, 1. So you can see that for these cases, the off-diagonal elements are 0. And for any other case, you will have some off-diagonal elements. And so the way that people interpret this off-diagonal element is that basically if there's coherence in the system, some kind of superposition, then you will have such elements. Okay. All right. Okay. But let's keep going. Okay. So now, so how do we include noise into the system? Then it's a little bit like what we tried before, except that now what we're going to do is use this density matrix. So again, let's think of this state where we have all these different states, and then there's one noisy state like here. So instead of writing the wave function, what we're going to use is we're going to write the density matrix for each of these. So we defined it in the previous couple couple of pages. So these ones are all rho, right? And then the one with noise is rho prime. And we're going to do the same thing as we tried initially. And now, essentially what we do is we average over these density matrices. And that is the density matrix of, this system. So what this sort of more or less is it's more like a kind of an average state of all these states. So what the density matrix allows you to do is, so before with the wave function, like you couldn't really do such a thing as an average state, because if you start adding them, then you're messing with the coherence and you end up with some weird results. But with the density matrix, you can do something like this. So let's just do the same example that we did before, just to make sure we're not getting any crazy results as we did last time. So, okay, so suppose it's half-half of these states, with the 0 as being one of them, and the 1 is the one with the error. Right? So if we do that, that's exactly the same case that we just tried before, where we ended up with this weird result. So in this case, the density matrix for the state without the error is just what I wrote here. So 1 in the top left-hand corner. And the one with the error, this one is this one here. And if we do half-half, then we're going to end up with this density matrix. Okay, and then if we compare to the state that was the superposition state, and if we look at the density matrix for that, it's simply this. And so we are getting something different this time, right? So that looks a little bit more healthy. And, it satisfies the properties of the density matrix that you expect. For example, the diagonal elements add to 1. So this is half-half, add to 1. Over here, also half-half, add to 1. This one is a state with noise, so you might expect that the coherence is sort of, there's no coherence in the system. In fact, it's a state that's made up of just zeros and ones, right? So we should definitely not have any coherence, because this doesn't have coherence, nor does that. So if we have a 50-50 of them, how can we end up with coherence, right? So it does not have coherence because these are 0. And if we compare it with the plus state, well, this one definitely is a superposition state, so this one does have coherence according to what we've got there. So anyway, it sort of passes the sanity check. So the more general definition, it looks like this. So this is basically the most general definition, I guess, for the density matrix. Yeah, it's the most general. So it's sort of like you have this collection of states here. They could be all different states. This is psi 1, psi 3, psi 2, and so forth. And they might all occur with some probability. And so what you do is you basically just sort of average over the density matrices, not the states, for each one of these different cases, and then you weight it with the probabilities. And that is your sort of average state system, or also known as the density matrix. So, so that's the final formula. Okay, great. So you might be thinking, this is one point that I think confused me for a long time, and I've heard other students get confused by this, so I know that I'm not the only one. So we've been talking about these ensembles, right? But you know, I don't, you know, what if I don't have an ensemble, right? So what if I've got this quantum computer? Okay, let's say I just got one qubit, right? And then I say, okay, the system, it's a noisy system because there's decoherence and there is you know, some noisy gates. So I don't have an ensemble. So how do I write my density matrix? It doesn't fit in with this picture. So actually, it doesn't really matter because you still can use it because, as I said, it's a kind of an average of the state, and of course, you know, you can do an average over literally, you know, if you just think about regular averaging, you know, you can take a bunch of what's a good example? Well, okay. I can't really think of a really good example at the moment, perhaps, except for some really weird examples like, so suppose, you know, you were like taking the average height of a bunch of people, right? So you go, okay, what's the average height of everybody in this classroom? Then you look at the average height of everybody, you know, divided by the number of people. Add up all the heights divided by the number of people. Or you could say, okay, what's sort of my average height over a 10-year period? You know, starting from when I was 10 years old to when I was 20. So of course you can just write down all your heights every year and then say, okay, my average height is like this. So you don't really need 10 people to take an average. You can still do it even if you've got just the one, you know, one person or one item. You know, it could be sort of in time, or it could be between different people. I mean, you know, you can still take an average either way. And so, because this density matrix is really just something like an average, you can also do it either way. So you can either say that, okay, I've got a bunch of them. These are sort of, you know, here's my collection of qubits. I want to know the average state of what all these guys are in, right? So you could do it that way. That's the way that we've been talking about, which maybe is the most intuitive way. But you could also think of it like, okay, here's my quantum particle source spitting out a qubit, let's say one every second. And then I'm over here receiving these qubits, and I'm saying, okay, what's the, you know, I'm getting one at a time, but what's the average state that I'm getting here? I could.
Longitudinal research. So we can measure the change that varies with time. So
Yeah.
We don't actually need a sample.
Yeah, well, I mean, your sample is sort of just over time, right? So because this is sort of like, you know, you're just receiving one every second or something. So it's still, you're still kind of averaging over something. It's just that you don't have them all at the same time. You've got one data point for one time, right? Whereas over here, you've sort of got the whole thing all there together. So yeah, so you can equally do it this way. Basically, you can do it kind of any way that you really like, you know, because basically, as I keep on emphasizing, this is kind of an average, right? So in whatever way that you want to take your average, then, you know, you can do that. So you know, you're free to go, okay, I'm going to average over that qubit, that qubit, that qubit, but not that one, and you know, okay, so you can do it that way if you choose. So it's just sort of more or less up to you how you are going to do your averaging. Right. What else has gone mad? Yeah. So we can. This is another very common way of doing it, and it sort of it's quite a common way of doing it, more or less because this is often how you do experiments. You know, you build your quantum lab, and then what it can do is it is, you know, sort of computer controlled and everything, and essentially you just run through the same thing over and over and over and over, right? Once you've set it up, just doing it a million times is usually, you know, kind of easy. So sort of like you run your experiment a million times, and then of that million times you're going to take your average. So this is kind of quite close to the experimental situation where you've built your experiment that it's spitting out, say, these atoms prepared in some state, and you're interested to know what is the sort of the average state that you're getting. And so in this case, you know, you would weight each of these different types of states by the probability that they are coming out. Okay, right. And another way that it can be used also is, all right, well, say I've already got a density matrix which describes sort of the average state of this set, right? And I've got another ensemble over here with another density matrix, maybe it's different, and also a third one. So then now I want to say, okay, now I want to calculate the density matrix average state of everything. Right? So what do I do then? Well, actually it's quite easy. You simply then just average over these density matrices themselves. So even though these ones consist of, say, individual atoms in some states, you can just do sort of averages of averages. So in the same way that you can just also do this with regular averaging, because when you know, say you've got like 3 classrooms, say, you know, 3 classes, equal sizes, right? And you know, everybody does an exam. You take the average score of an exam, class 1, class 2, class 3, and then you say, okay, what's the average score of the whole group? Then of course, if the classes are equal size, then you just have to take the average of the averages, and that's the global average. Right? That all works out mathematically because, well, yeah, I think you guys. So taking averages of averages still is another way of working out the total average. So exactly in the same way, you can still you can do that here. So you take the sort of the sum of the density matrices, and then you weight it by the sort of the probability of each one. So in this case, well, you know, if you've got sort of the same, well, if you've got one sample, then and they're all equal sizes, then the probability would be sort of 1/3. But of course, if one ensemble is bigger or something, of course that would be taken into account in this factor. And that works out well because total density matrix. Well, let's just write it out. Okay. So so here's the density matrix of one of the ensembles. So what we're going to do is we're going to label it like this. So what this means is, so this sum, n, is over the individual atoms within each group, right? So say we're doing group 1, and then so this n would be running over, it'd be like n equals 1, 2, 3, 4, 5, 6, 7, like that. And there's three different, so this probability is a probability within that group. So this, we've got row 1, then probability brackets 1, n means the probability of that happening within this group, and psi n with m means the nth atom within the mth group. So group 1, atom number 10, is that state. Okay, and then so the density matrix of the whole thing, I've said is P. So maybe I'll use different P slightly. Is equal to this. So we can substitute it all in just to see what it all looks like. And we've got the probability of the mth group happening. This is the probability of the nth atom within the mth group. So it looks like this, and so this sum over m and n, so basically the combination of these two sums runs over this whole set, because if you, this m, for example, goes from 1 to 3, right? So you run through all three groups, and then within each group you run through every atom. So this sum will run through the whole thing. Then you have this product here, which is the probability of the group. And then you've got the probability of the nth atom in the nth group. So in other words, it's sort of the, if you think about it, it's like, this is like group 1, group 2, group 3. This is the probabilities of that happening. And then the probabilities in M are like all the probabilities in there. So you have this sort of tree where you multiply the probabilities. And so the total probability is here. This is actually more like a conditional probability, right? Because you know that the total probability is like the conditional. Yeah, so the total probability is going to be, like, say, for here, like P1, and well, if it's like the nth atom in the first group, then it will be that. So that's the probability of that particular atom or that state happening, and then this is the label for the nth atom in the mth group. Make sense? Okay, so let's do a little practice. So let's say a machine produces the state 0 25% of the time, state 1 25% of the time, and then the state minus 50% of the time. Then find the density matrix of the qubit. something?
I just find something where the trace is not one.
Oh. Okay, what did you get for, so it's this state 25% of the time, this state 25, and then the minus state, what did you get as a minus state?
1 minus 1.
1?
Yeah, the diagonal is
Ah,
is 1 and the rest of them are minus 1.
like this?
Yeah.
Okay. Any factors? Any factors?
Yeah, a half.
Ah. Yeah, okay, so that looks right. And essentially you just multiply by half, multiply by quarter, and add them together. So should be so yeah, so this on the diagonal, this will be quarter, and quarter up there, so this should be a half. This should be half and what's a quarter? So I brought up this before. Seems
The
right.
diagonal should be equal to.
Because you add this quarter to this quarter,
Oh yeah.
yeah, and this quarter to this quarter. So maybe that was what was missing.
Yeah.
Yeah.
I forgot the coefficients.
Oh right, the probabilities. Yeah. So these are the probabilities that you need to weight the density matrix by. Yeah. So that gives the same answer there. Okay. Okay, and all right, that's for a qubit. What about for composite systems? So, say Alice and Bob have some potentially entangled qubits between them, and say they've got a bunch of them and they're all maybe a bit different, again due to noise or something. Or maybe simply just because they've got a bunch of qubits and they want to average over for whatever reason. So yeah, so these could be entangled states or product states or anything. So this could be anything. So yes. So basically, yeah, it works in the same way. You can just average over these states in the same way. So as a special case, so what if Alice and Bob each have a bunch of qubits, but suppose they've never been in contact with each other, you know, they don't know each other, they're on opposite ends of the earth, and so these are kind of independent quantum states. So you might remember when we're doing the lecture on composite systems, we talked about independent states, and basically if you have an independent state, then for the pure state case, it basically is just like takes this kind of form. And what about for mixed states? So basically it's something similar, but we have to do it for the matrices, for density matrices. And well, firstly, let's say that the density matrix for Alice is something like this. This is just what we've been talking about. And Bob has something like that. And so for independent states, it has this so-called tensor product structure. And what that actually means is that the individual states have a tensor product like this. So when you substitute this into here, then basically each of these states are in this tensor product. So is that's the Kent, so this is bra. And secondly, these probabilities are also in a product form. So maybe the key feature here is that in order for the density matrix to be in this completely independent form, what you need is that, so the states need to be in this product state. So that was just what we had before. But not only that, we also need the probabilities to be in this product form, because we know from classical probability theory that independent probability distributions have to be like a product form in order for them to be, well, independent. So, okay, so that looks a little bit complicated, so let's just maybe do an example to clarify that. Okay, so we can look at let's look at some sort of special cases. So suppose it was a so we can look at certain cases. So we can look at a classically correlated state, and so a classically correlated state just means that you know, there's no kind of entanglement or anything like quantum mechanical, so there's no correlations because of quantum correlations. So for example, that could be something like this. So suppose with probability half, there's two qubits that are in this state, probability 1, they're in this state. And this of course just means that, this means this. So, you know, what this means is that I think, you know, when we were talking about composite states, I had some kind of funny example. You know, there's some kind of gun here, and then here was Alice, here was Bob, and this gun was shooting, say, green balls and well, a red pen, and black balls, just randomly, right? And for example, if the black ball was, say, 1, and the green balls were 0, and say this was 50-50, then this would be like a classically correlated state, because obviously we can have just regular correlations, you know, when two things happen always at the same time. This is what we mean by, well, that they're correlated, right? So it's classical correlation. So this type of situation we would write as a density matrix in the following way. So we find the density matrix of this one. So that's the state. The density matrix of, well, okay, it's too squished. So the density matrix of this one you would write as 0, 0, like this. And the density matrix of this state you write as 1, 1, like that. And then what you do is just average over those two density matrices. So that would be an example of a classically correlated state. And just if we write it in terms of that that kind of form there, then so let's sort of write it in terms of this sum. So suppose the first qubit runs from 0 to 1, and the second one also runs from 0 to 1. And then let's write this sort of more generally, so Pn n dash. Okay. And so because there's only terms like 0, 0 and 1, 1, this thing is a 4 by 4 matrix. And so the only terms, what this matrix looks like is, this is not a density matrix, by the way, just writing the coefficients. Yeah, so it looks like this. And this probability distribution, you can't write in this way, right? So there's no way of writing that, this probability of having 0, 0 and 1, 1 in this product form, like here, because, well, yeah, I mean, this matrix cannot be written in this kind of product form. So, yeah. Another way of saying that is that this probability is like, it's correlated. So if it's correlated, you can't write it as independent probability distribution. So basically, you cannot write this as Pn prime B. So there's basically no way of writing this distribution in this way. So that's a kind of a classically correlated example, and this is an example where it's not, it's not this independent distribution, and it's not independent because it's like, there's anything quantum. It's actually, it's not independent because they're correlated, right? So they're correlated particles. So you cannot sort of consider A and B as separate because things are happening in correlation. So that's classical correlation. So basically the fact that this probability distribution here is this product form is one of the reasons why this is independent. And then the second case is, it's like there's some quantum correlation. So if the state, for example, between Alice and Bob was, say, 0, 0, say, 1, 1, we said before that basically there's no way of writing this as some state like this. This one we did. And so because the state here looks, we're saying it has to be of this form, and we can't write the state in that form. Again, it can't be independent. So these are two sort of examples of states, and so that we could have the probability of this one just being 1 in this case. Like if we're making a density matrix, we just have a pure state of this Bell state, and it would not satisfy basically this form. Yeah. So these are just two examples of states that are not independent states, and they're not independent for this example because it's classically correlated. It's not independent in this case because it's quantumly correlated. And of course, you can have both cases at the same time. So you can have both quantum and classical correlations, and it also wouldn't be of this form. Questions? Okay. Right. So maybe we just finish up and do this question. So say we have this situation where Alice and Bob shares pairs of qubits, and half of them are in this Bell state, and the other half are in this product state. So find the density matrix of the composite system. Actually, I think maybe we should leave it there, in fact, because we're sort of out of time. So maybe we'll discuss this first thing next lecture. So why don't I leave it as a kind of a homework for next lecture? Okay. Okay. All right.